Hello everyone, my name is Xizi Wang. Today I am going to present our paper exploring visualizations for precise guiding bare hand gestures in virtual reality. This is a collaborative work with Ben Lafreniere and Jian Zhao from the University of Waterloo and Meta Reality Labs. Bare hand interaction plays an important role in immersive augmented reality and virtual reality systems. It is natural and intuitive, and it provides rich interactions and conveys social cues in many scenarios, such as object manipulation, game interaction, and communication. However, hand-tracking errors are avoidable during gesture performing, and these errors are ruining users' experience in AR and VR. Previous research has shown that visualizations are helpful for guiding users to move their hands or arms, and the current solution to help users learn and perform a hand gesture is providing detailed visual description in the onboarding phase. However, limited study explored micro-level visual guidance for precise bare hand gestures in AR/VR. So in this work, we investigated different visual guidance that can facilitate users to perform precise static pose gestures in VR. So the first question we came up is how to design visual guidance. To answer this question, we conducted a mixed method formative study. We interviewed 5 VR users with 1 to 5 years VR experiences. We analyzed and came up with 4 types of information that users need to correct their gestures: arrow, target, direction, and difference. Based on this, we designed 15 visualizations. Each combines different numbers and types of information. We use balls to represent location of arrows and targets, lines represent directions, and the length of the line represents distance between arrow and target. So for example, V134 contains the information of arrow, direction, and difference. The orange ball indicates that a joint of the middle finger is placed incorrectly. The line extending from the orange ball shows the direction the user should move, and the short length indicates that this joint is close to the target position. Meanwhile, the purple ball shows that 2 hands are not aligned properly, and the 4 lines extending from these purple balls show the directions in which adjustments are needed and the severity of the misalignment. We then cross out 7 visualizations, since they don't contain the arrow information, and these visualizations look complicated and information overwhelming. So next, we conducted the second part of the formative study and recruited additional 6 participants with different levels of VR experience to watch videos and rank these visualizations. Then we selected the best of 4 visualizations, one from each complexity level, and refined them based on participants' feedback. Now we rename them as VG1, VG2, VG3, and VG4. The number represents the number of information this visual guidance contains. Let's take a close look at these 4 visualizations. So the VG1 contains only the arrow information, where orange balls on the joints represent which joint is not placed properly, indicating an incorrect pose. For double-handed gestures, the purple outline balls indicate which part of the hands are not aligned properly. VG2 contains 2 types of information. Compared to VG1, it has the additional information of direction. The line extending from the orange and purple outline balls guides the user to move to the target position. VG3 contains 3 types of information. You can consider it is built on the VG2. It looks similar to VG2, except that the length of the line will change depends on how far they are away from the target positions. VG4 has the most information. The orange balls indicates the incorrect joint in the pose, while the green balls show their target positions. There is a line connecting the arrow position and the target position, indicating both the direction to move and the distance between them. Similarly, for double-handed gesture, the purple outline balls indicate which part of the hands are not aligned. The connecting lines also indicate how to move and the degrees of misalignments. Here are some more demos for single-handed gesture and double-handed gesture. Next, we would like to know whether the visual guidance is helpful and what are users' perceptions regarding various micro-level visual guidance. To answer these questions, we conducted a within-subject controlled experimental study with 15 participants. Each participant performed a total of 20 gestures that have been used or explored in commercial applications or previous research projects under 5 visual conditions. To eliminate immediate carryover and learning effect, each participant performed 2 single-handed gestures and 2 double-handed gestures for each visual conditions. And the order of the visual conditions and gestures are counterbalanced. So for each task, participants switch between idle gesture to a target gesture within 60 seconds for 2 times. Once all joints are within the threshold for 1.5 seconds, we consider the participant successfully completed a gesture performing task. From the study, we find a significant difference in target completion time between no VG and 4 types of visual guidance. This indicates that all types of visual guidance is helpful in performing a hand gesture more quickly. We also find a significant difference in average sum of offsets between no VG and VG2 and between no VG and VG4. These results suggest that with VG2 and VG4, users can perform a double-handed gesture more precisely. To further investigate the visual guidance, we categorize the gesture into 3 groups based on the difficulty rankings provided by participants. Our findings reveal that only the visual guidance with minimum information, which is VG1, significantly facilitate users to perform low difficulty gestures more quickly. And all types of visual guidance significantly help the users to perform moderated difficult gestures more quickly. For high difficulty gestures, users provided with VG4, which contains the most information, perform the gesture more quickly than with no visual guidance or with VG1. So based on these insights, we recommend designers or developers may choose different types of visual guidance for gestures with different levels of difficulty. Also, we find that VG2, VG3, VG4 reduce overall workload during the gesture performing tasks. Specifically, they reduce the mental workload, increased performance, decreased effort, and frustration. Furthermore, we find that using visual guidance, participants feel significantly more confident in performing the gesture task. Especially when provided with VG4, participants saw that the hand tracking and hand gesture recognition system is more reliable. In addition, we collected qualitative feedback of the participants. When no visualization was provided, participants felt frustrated, confused, tougher, and less effective to perform a correct gesture. These feelings were magnified when participants were performing double-handed gestures. We also find that providing more information may not always be helpful. It can reduce confusion, but it could also raise the problem of information overwhelming and distraction. There is a trade-off between the amount of information and the workload in processing the information. In this work, we explored and evaluated different types of visual guidance, finding them beneficial in improving the speed and accuracy of static post-gesture performance, reducing their workload, and more. And looking ahead, We identified potential future work in extending our exploration to visual guidance for other types of gestures, such as dynamic pose gestures, and other visual encodings, such as ghost hand and heat map. We also envision the opportunity to integrate the micro-level visual guidance with detected user intention, helping users to learn and adjust their gestures more effectively, not only during the onboarding phase, but also in the daily use. For more results and details, please see our paper.